welcome back to my channel. Today we'll continue to learn chapter 13, gas law and kinetic theory. So in this video, we will continue to discuss with 13.3, molecular kinetic energy and internal energy. Exercise 4, questions number 1. Estimate the average mechanical energy posed by the molecule in the carbon dioxide at the temperature of 300 Kelvin. Okay, so since we have the temperature and also here the main question mentioned a molecule. Okay, and a molecule meaning that N is equal to 1, and carbon dioxide actually is polyatomic. Okay, so meaning that the degree of freedom is equal to 6. Okay, now we want to find the mechanical energy, meaning that we want to find kinetic energy. Okay, so we can find kinetic energy equals to F over 2 nRT. Okay, where because this is a carbon dioxide, so polyatomic for the degree of freedom is equal to 6 over 2. Okay, N is the number of mole, where we have the number of mole. Okay, number of mole is equal to number of molecule over number of Avogadro. Okay, so we can write as 1 over 6.02 times 10 to the power of 23. And R is 8.31, temperature is 300 Kelvin. Okay, so the final answer that we will get for the mechanical energy is 1.24 times 10 to the power of negative 20 joule. Question number 2, determine the average kinetic energy of the gas, meaning N is equal to 1 at the temperature of 300. Okay, so these are the information we have. N equals to 1 and the temperature is equal to 300 Kelvin. So the first one, we want to find the kinetic energy. Okay, helium. Okay, helium is a monoatomic. And the nitrogen N2 is actually a diatomic. Okay, so for monoatomic, the degree of freedom is actually 3, and the nitrogen, the degree of freedom is 5. Okay, so we go to questions 2A first, where we want to find K average. So K average is equal to 3 over 2 nRT. Okay, so 3 over 2 n, because our n, the number of mole is equal to the number of molecule per number of Avogadro, so we can write 1 over 6.02 times 10 to the power of 23 times 8.31, and the temperature is 300. Okay, so the answer that we will get for helium is equal to 6.21 times 10 to the power of negative 21 joule. Okay, so if let's say you want to use another equations, K equals to 3 over 2 nKT, also you will get the same answer. Okay, so you can try where n equals to 1 and K is equal to 1.38 times 10 to the power of negative 23, and the temperature is 300. Okay, so similar, you will also get the same answer, 6.21 times 10 to the power of negative 21 joule. Okay, next we will go to nitrogen, where nitrogen is the diatomic. Okay, so we can use K equals to 5 over 2 nRT. Okay, so we substitute. N is 1 over 6.02 times 10 to the power of 23. R is 8.31 and the temperature is 300. Okay, so we will get 1.035 times 10 to the power of negative 20 joule. Okay, so if you, let's say you want to use another equation, 3 over 2 nKT, okay, you will also get the same answer. Okay, where K is 1.38 times 10 to the power of negative 23 and the temperature is 300. Okay, so the answer is 1.035 times 10 to the power of negative 20 joule as well. Okay, so next we will go to questions number 3. Okay, question number 3, a vessel contains of hydrogen 7.5 times 10 to the power of 17 molecules per unit volume. Okay, and the root mean square of the molecule is 2.5 km per second, and the temperature is 30 degrees Celsius. Okay, so they give you the molar mass, the number of Avogadro, and also the value K constant. Okay, so number 1, determine the average translational. Okay, so if you look at this word translational, meaning that only linear. Okay, so meaning that our the degree of freedom must equal to 3. Okay, for monoatomic, diatomic, or polyatomic, because of the word translational, meaning that we only consider the linear. Okay, the linear. Okay, so now we want to find the K translational. Okay, and the equation is equal to 3 over 2 nKT, or you can use 3 over 2 nRT. Okay, depends on what are the informations we have. So first, what are the informations we have here is we have the molecule per unit volume. So the molecule per unit volume is equal to 7.5 times 10 to the power of 17. And also we have VRMS, okay, is equals to 2.5 kilo. Okay, so we must times 10 to the power of 3. And the temperature is 30, so we must plus 273.15, change it into Kelvin. Okay, so these are the informations we have. Okay, so since the question mentioned a molecule, so meaning that the N is equals to 1, okay, so we can use either one. So let's say I use 3 over 2 NKT, N is 1, K is 1.38 times 10 to the power of negative 23, and the temperature is equals to 303.15. Okay, so we will get 6.28 times 10 to the power of negative 21 joule. Okay, so this is the translational kinetic energy. Okay, next we want to find the pressure of the hydrogen gas. Okay, so as we learned in the last video, okay, our pressure is equals to 1 over 3 Nm over volume times the mean square speed. Okay, so we substitute 1 over 3 N over V. Actually here already give you, okay, so this N over V already give you 7.5 times 10 to the power of 17. Okay, but the mass, we don't have the mass, but we can find by using the equations. Okay, so since the number of mole is equal to mass per molar mass and also equals to number of molecule per number of Avogadro. Okay, so we can find mass, okay, by using equation, the number of molecule per number of Avogadro times the molar mass. Okay, so our number of molecule is 1, number of Avogadro is 6.02 times 10 to the power of 23, and the molar mass for the hydrogen is 2 gram. Okay, so 2 gram I convert into kg. Okay, so the mass of the hydrogen gas is 3.32 times 10 to the power of negative 27, so we substitute into the equation. Okay, times the mean speed, mean square speed, where mean square speed we only have the V average, VRMS. Okay, so VRMS here, we can find the value here, meaning that we square it up, 2.5 times 10 to the power of 3, then we square. Okay, so you will get mean square V. Okay, so the final answer we will get 5.19 times 10 to the power of negative 3, and the unit is Pascal. Okay, next one, question number 4. A vessel contains an ideal diatomic gas, temperature is 20 degrees Celsius, and the total translational kinetic energy is 3 times 10 to the power of negative 6. The mass of the gas is then double, and the total translational kinetic energy becomes 9 times 10 to the power of negative 6. Okay, so determine the new temperature. Okay, so meaning that here we have before and after. Okay, so from the questions, they already told us that this is the translational kinetic energy, where the degree of freedom must equals to 3. For monoatomic, diatomic, and polyatomic also, the degree of freedom is 3 because it's only involved translational. Okay, so now we have two cases. Case 1 is when the translational kinetic energy is equals to 3 times 10 to the power of negative 6. Okay, the temperature is equals to 20 degrees Celsius, so I plus 273.15. Okay, and the mass initially is M1 is M. Okay, now when M2 double up, meaning that become 2M, the translational kinetic energy become 9 times 10 to the power of negative 6 joule. So we want to find the new temperature, we want to find T2. Okay, so we know that for translational kinetic energy equations, K equals to 3 over 2 nRT, okay, where N here is equals to mass per molar mass. Okay, so actually we can do it ratio because we have two cases. So K1 over K2 is equals to 3 over 2 nR T1 over 3 over 2 nR T2. Okay, so 3 over 2 we can cancel, R and R we can cancel. So finally, K1 is 3 times 10 to the power of negative 6. K2 is 9 times 10 to the power of negative 6 equals to N. Okay, N is equals to mass per molar mass. And the first one, temperature T1 is equals to 293.15. Okay, and N2 is equals to M2 over molar mass. And this is the temperature that we want to find. Okay, so since they are the same gas, so the molar mass we can cancel off. Okay, so our equation we can get 1 over 6, 10 to the power negative 6, and 10 to the power negative 6 we can cancel. So it becomes 1 over 3 equals to M 293.15 M over T2, and M2 is equals to 2M. Okay, so later M and M we can cancel. So final answer T2 we will get 439.73 Kelvin. Okay, so this is the new temperature. Okay, so that's all for this chapter. We'll continue with the new chapter, chapter 14, thermodynamic. Okay, so see you on next video. Bye.